में एक ही ऐप है।
क्या sorry I zoned out.
No problem. अरे topological में when you do DFS वाला topological, you can get multiple solutions. When you use cons, you get only one unique solution. So this is like the benefit of this.
So you go to the one that has 0 invert at first, right?
You just make an array of every element and you write the value of number of inward arrows on every element.
Yeah, in degree.
In degree, yeah. You put every element with 0 in the stack.
Okay.
And you keep on popping them out.
So the only thing could be if there are 2 or 3 that become 0 initially. So
you follow the in degree
the stack order. So if you visited like let's say 1 or 5 0 हो गया initially. तो stack में 1 गया फिर 5 गया तो 1 5 से होगा.
1 गया 5 गया तो 5 पहले pop out होगा because
fragment of but the right answer could also be 1 5. So तो अगर in your topological only तुम 5 पहले add किए हो while coming across, so then वो add हो जाएगा. तो फिर 1 5 आएगा तुम्हारे खान के algorithm से भी.
मतलब
the way you it goes in the stack. Yeah.
The way it will come up. Okay, so hello everyone, and today me and Raj are going to go over some of the topics which are considered really important in graphs. So we'll be covering some basic information about graphs, and we'll be covering depth first search, which is included in topological sort, and then we'll be covering uh, Khan's algorithm. So um, graphs are basically when two states are related to each other and they are connected either directionally or non-directionally. So being connected direct example of being connected directionally can be when internet is set up between two destinations. So we tell that destination A should give internet to destination B. Let's say you have a router in one of the rooms, and then you have another, you plan to have another router in one of the different rooms. So you'll connect point A to point B. So that's kind of a graph. So that's a directed graph. And the utilization of directed graphs and graphs on general can be found in the form that whenever we write a program, we write header files, right? So every header file includes libraries. So those libraries are prefetched and pre-processed so that we can use those libraries and write the code. So in that way, we can imagine a graph. So a graph enables us to do what we want to do by loading the prerequisites which are required. So a similar example of graphs can be social networking graphs. So we all have our accounts on Facebook, right? And we all see mutual friends between two people. So let's say if me and Raj are friends, we'll be able to see some of the people who are mutual friends between us. So how is this possible? This is possible because the friends that Raj has and the friends that I have, they are connected in the form of a social networking graph. And those graphs are matched, and the union between those graphs are given to us as the mutual friends that we have. So this is kind of like an intro to where graphs are used in real life scenarios and why graphs are important, because it can seem really vague that why are we touching on this topic and why are we studying this. So we'll be going over some of the topics, as I told, topological sort and Kahn's algorithm. So Raj, what do you think about graphs? What are your thoughts on?
Hi, Shivanku. So graphs are a really powerful way. You see it everywhere, and they help you do a lot of operations really fast if you know how to model a graph. And I think the examples that you gave were really good ones about friends in Facebook. Another example that I can also come across for graphs would be uh, the internet. So each website is actually a node or a vertex in the graph. And if one website links to another website or a web page, they have an edge between them. So two web pages are linked by an edge. And so that's another good modeling of a graph. And we also see another example can be the classes and prerequisite relationships at college. So each class can be a vertex, and if one class is a prerequisite for another class, they have an edge connected between them. So that's another example of a graph. So Shivanku, I was wondering, what are the what are the ways we can traverse a graph?
I think the different ways can be, we can do a depth first search or we can do a breadth first search.
Can you tell me more about depth first search?
Yeah, sure. So when we do a depth first search, what we do is we go from one node and we keep on traversing till we reach the leaf node. By that, what I mean is, let's say we are at a node A, and A connects to B, B connects to C, and D is the leaf node. So we'll go all the way from A till the leaf node D, and then recursively backtrack till A while covering all the child nodes of B, C, and D. Am I right?
Absolutely. You make a really good point. And what is the breadth first search as well?
Oh, so in breadth first search, what we do is we traverse nodes level by level. So what we'll do is it's similar to something that we do in trees as level order traversing. So what we do is we traverse all the nodes which are at a particular level, and then we go to the next level and traverse all the nodes which are present at that level.
Yeah, so if I start a breadth first search, and okay, I've started sharing my screen. So if I start a breadth first search on node 1, I first go to all the nodes that is connected to. So I visit 2, 5, and 3. And then when I visit 2, I add the children of 2 to a queue. When I visit 1, when I visit 5, I add the children of 5 to a queue. And when I visit 3, I add the children of 3 to a queue. So once I have finished traversing 1, 2, 5, and 3, I have added the children of 2 to the queue initially. So I go to 4 and I see that 4 has no children. So, I'm done with that. I move on. I move to the children of 5. 5 had a child of 6. So I look at 6 and I see that I'm done because 6 is not connected anymore to anything else. I move on to 3 and I see that 3's child is 5, but I've already visited 5, so it does not matter. And that would be the breadth first search traversal from node 1. Okay, so moving on. So these were basically the 2 ways you can traverse a graph. And the main reason why we're here today is we want to talk about topological sort. So there's a relationship between 2 graphs, and as I mentioned, one of the examples of a graph could be classes and their prerequisites. So, and they are related. They have an edge between them if one class is a prerequisite for another. So if I wanted the order in which a student should take a student who takes 1 class a semester, the order in which he should take some particular number of classes, that is called a topological sort. So for example, if I have 4 classes, English 1A, Calc 1, Calc 2, and Calc 3. So Calc 1 is a prereq for Calc 2, Calc 2 is a prereq for Calc 3, and English 1A has no prerequisites. So I need to take Calc 1, 2, and 3 in an order, and that's the order, like I said, but English 1A does not matter. So topological sort would mean having an order between any 2 pairs of vertices, but there could be other vertices that have no particular order or relationship between them. And we're going to see now how we can traverse graphs, or how we can traverse a graph or look at a graph and get its order. So here you can see this graph. We'll use the same example, the same graph as before. We need to figure out an order in which, let's imagine all of these different nodes are classes. And we need to imagine how we can take the classes in a particular order. So one way I'm going to talk about, there's 2 different ways you can do this. One is the Khan's algorithm, and the other is by depth first search. So I will be talking about depth first search first. So, okay, let's look at the adjacency list representation of the same graph. So here it is. All of these are classes 0, 1 through 7. And when I look at 0, I can see that 0 has a prerequisite of 3. When I look at 1, I can see that it has a prerequisite of 2, 3, 5, and 6, and so on. So if I want to get the order in which I take these classes, I can run depth first search on any given node initially, and I can run that search on the whole graph as a whole. And the answer to the solution, how it actually comes up in the sort, is that the finish time for each node, when they're sorted in, when you sort the finishing times of each node, that's going to be the topological order. So let's go back to the graph representation, and let's start with node or vertex 0. So when I run that first search on vertex 0, I go to 3. I go to its neighbors 3. So I go to 3, as you can see. I now go to, from 3, I go to 5, as you can see that. I run DFS on 3. Now when I run DFS on 3, then I run DFS on 5. And you can see the order of the stack calls on the right-hand side. I go to 5's neighbor 6, and I run DFS on 6. And you can also see the finish times being here. So the little f equals 5 is the finish time for it. So 6 was done, so I added 6 to my topological order. The call comes back to DFS of 5 because I finished that first search on 6. When I'm at 5, I see that it has no more neighbors, and I have finished 5 as well. So 5 got added to my topological order. Now I go back to 3. So I see that I am done with all the children of 3. 3 is finished at that first search, and 3 gets added to my topological order. Now I go back to 0. I am finished with 0. So 0 gets added to my topological order because 0 had no more children. So now I move on. So I need to run depth first search on the whole graph. And we started off with node 0. We finished all the recursive calls that were possible from 0. And now we move on to the next node in all our vertices. So the next node would be 1. And I run depth first search on 1. So I go to the child of 1, that's 2. 2 has a child 4. So I run DFS on 4. 4 is done at this point. So I added it to my order. My recursive call goes back to 2. 2 now goes to the next child, 5. But 5 is already done. So the recursive call now goes to 6, then the other child of 2. 6 is already done, so the recursive call goes back to 2. 2 is done. 2 gets added to my order. I now go back to 1. 1 goes to 3, because 3 is the other child. 3 was already done, so the call goes back to 1. It goes to 5. 5 was already done, and goes back to 1. It goes to 6, because 6 is already done as well. So it goes back to 1, and now I'm done with 1 at this point. So I add 1 to my order, and I'm done with that. So I move on to the next node being 7. I see that it's done, it has no children, so I add 7 to my order, and then that's it. I have my topological order using depth first search. So when you're using depth first search, you can do it by recursion, but this was a small graph. If we make it complicated, like this large graph, doing it by recursion would increase the number of calls to the program stack, and you could come with an error overflow of the stack. So what you want to instead do is actually have your own stack to do this. And we'll take this more complicated example and see how the DFS, the topological sort works in the DFS with this. So we are starting with 0 and we go to 1. From 1, we go to 2. We're done with 2. So we add it to the order. We go back to 1. At this point, we're done with 1 as well. So we add 1 to the order. We go back to 0. We go to the next child of 0. That is 2, but we see that we are already done with 2. And then we go to the next child, that is 14. We're done with 14 here because 14 has no more children. So you can see there's a finish time of 7, and we add 14 to the order. We go back to 0. At this point, 0 has no more children, so we are done with 0, and we add 0 to the order. Now we start our depth first search on the next node, that was 3. 3 has no children, so we are done with 3. We add it to the order. We move on to the next node, 4. On 4, we see that 4 is connected to 5. So we run that first search on 5. We see 5 is connected to 6, so we run that first search on 6. 6 is connected to 10, we run it on 10. 10 is connected to 17, so we run it on 17. At this point, we see that 17 has no more children, and we're finished with 17, so we add it to the order. We go back, we see that 10, we're done with 10, we add it, it's finished, we add it to the order. We're done with 6, so we finished it and we add it back to the order. Now we go back to 5, we visit the next child of 5. And you can pick a child randomly. In this case, we pick 8. So we move on to 8. We're not done, so we move on from 8 to 11. 11 has children, so we move on from 11 to 12. At this point, we see that 12 has no more children, we're done, so we add it to the order. We go back to 11, we go to the next child of 11, that is 14. It was already done, so we don't do anything. We go to the next child of 11, that's 15. 15 is connected to 16. We have no more children from 16. We're done with 16, so we add it to the order. We go back to 15. We're done with 15 here. We finish, so we add it to the order. We go back to 11. At this point, we're done with 11 as well, so we add it to the order. We go back to 8. At this point, we haven't visited 12. So we look at 12, but 12 is already done. So we're done with 8 at this point. We add it to the order. We go back to 5. And you can see the blue arrows are the ones that we have visited, and the black ones show that we still have to go there. So now we go from 5 to 9, 9 to 13, 13 to 16, but we've already finished 16, so we don't do anything. We go to 17, we've already finished 17, so we don't need to do anything. We're done with 13 at this point, so we add it to the order. We go back to 9, we're done with 9 at this point. We finish it, so we add it to the order. We go back to 5. We're done with 5 at this point as well. So after getting done with 5, we add it back to the order. We go back to 4. At this point, we're finished with 4. No, we need to go to 7, I'm sorry. So we go to 7, and 7 has no more children, so we are done with 7. We add it to the order. We're done with 4 at this point, and we add it to the order. Looks like we finished the whole, and that's how we got our topological order for this big graph. So you can see that even with the bigger graph, it works. It works just fine. And you can have multiple different orders. There's no one unique order, because when you visit a node, you can choose to go. You can go to any one of its children. So depending on which child you go to, you would get multiple different combinations, but each combination would work if you run the depth first search correctly. So that is topological sort using depth first search. And we know that there's multiple ways. There's another way where you can do it. So the other way is by Khan's algorithm. So that's a little different. And that, Shivanku is going to go ahead and explain that topological sort using Khan's algorithm. So
before I do that, I'll just give you guys a minute to process what Raj explained to you guys about topological sort, so that if you have any questions, you can send us the questions in the chat, and then we can try to address your questions through our discussion. Also, post that, I'll be explaining to you guys Khan's algorithm, and so you can take like a minute or two to process what he just explained, and then you can go ahead and then we can probably go ahead if you guys don't have any questions, and so on. So this demands for a solution which can give us a unique solution, right? Because we can be in a situation where we want only one kind of solution. Let's take my Facebook example for that matter. So when Raj and I have some friends in mutual, we don't want those list of friends to change. That list stays the same, right? Because overnight our friends are not going to unfriend us, or it's not as if we have them in common, but they show them in his list but not in my list, right? So there are some situations which demand sort to return a result which is absolutely the same no matter what, given some graphs or some states, right? So topological sort is not suited for such situations. It is fine for situations like taking subjects, because you can take any number of subjects from a bucket, right? So it is fine for those situations, but for the situations in which we need a particular situation, I'll share my screen and show you how we can we can do using Khan's algorithm.
So Shivanku,
I have a question here. How do you decide which case you can do it? I remember something about a directed or undirected graph. Is that what you were hinting at?
Yeah, so that is one of the things that I was talking about. That one thing, it needs to be a directed graph. The second thing, the graph should be acyclic. So it should be a DAG, directed acyclic graph. Only then these methods can be used in order to obtain a topologically sorted array. Okay, so what happens in Khan's algorithm is, how it is different is that we take an array of in degree. So we have made an array. In degree over here means the number of inward arrows on any state. So let's say 0 has 0 inward arrows, so we'll put 0 over here. 1 has 1 inward arrows, so we'll put 1. 2 has 0 inward arrows, so we'll put 0. 3 has 1 inward arrow, so we'll put 1. 4 has 1 inward arrow, so we'll put 1. 5 has 0 inward arrows, 0. 6 has 2, so we'll put 2. And 7 has 1, so we'll put 1. So if I click to do topological sort, I can also show you these. So I've initialized everything to 0. As I'm discovering the inward arrows for every number, I'm increasing the count. So for 6, these are the 2. For 7, this is the 1. So you see the resulting array afterwards. We have 0 for 0, 1 for 1, 0 for 2, 1 for 3, 1 for 4, which is this one, 0 for 5, nothing, and 2 for 6, which are these one, and 1 for 7. Okay, so this is something which is easy. The next step is all those which have zeros. All those which have zeros, you'll push them into a stack. Okay, so we'll push 0, and then we check which one is 0. Okay, second, so we push 2, and then we check, okay, which one is 0. Then we push 5. And you remember the property of stack. What goes in, the top always comes out, right? So if I push 0, 2, and 5, so which will be the first element, Raj, to be popped out?
The first element to be popped out would be 5.
Yeah, exactly. So the first element to be popped out would be 5. Let's show you guys what I'm talking about. So see, here we have made a stack. So now what happens is we'll pop out 5 from this stack, and along with that, we'll remove all the outward arrows that are going away from 5. Since there were none from 5, so we move ahead. Now we'll pop 2. Okay, and then again we remove all the outward arrows which are going from 2. So since in this case 2 has an outward arrow to 6, so in this in degree array we remove the count of 6 from 2 to 1, like this. Okay, I'll repeat myself again. So if we have a state, when we pop that state out from the stack to the result, along with that all the outward arrows, we'll count those outward arrows and remove that from the in degree array. So since we had an outward arrow from 2 to 6, we made the count of in degree for 6 from 2 to 1. Okay, so the next step is again search if there is an in degree which is 0, so that we can push those into the stack. We again check, is anything 0 that we have already not added? No. So we stay with the result. Now what do you think next would happen? So what happens is we pop 0 out and we check which are the outward arrows which go from 0. So we have 2 outward arrows, right? We have 1 and which we have 1 that goes to 4. So we'll remove the count for 1 from 1 to 0, and we'll remove the count for 4 from 1 to 0. Let's see how it happens. So 0 goes in the result. We check, okay, 0 points to 1, we remove its count. 0 points to 4, we remove its count. And then we again check the in degree. So now we have 2 new elements which are 0, right? So 1 became 0 and 4 became 0, which means 1 will be pushed into the stack, 4 will be pushed into the stack, right? So 1 is pushed, 4 is pushed. Now, again, we follow the same thing. Now we pop 4 out. If we pop 4 out, we have 1 outward arrow from 4, which is 6. So we'll remove the count for 6 from 1 to 0, like this.
So Shivanku, now that we see that 6 has become 0 as well, what do we do in this situation?
Good question, Raj. So basically what we'll do is we'll again search. So after every change that we make in the in degree array, we always scan it to check if any element has become 0. Because whenever any element becomes 0, we push them into the stack. So the answer to your question would be, since 6 became 0, we'll push 6 into the 0 in degree vertex stack.
Is it necessary to scan the in degree array always to check find zeros? Can we, so when we took out the, when we reduced the in degree of 6, we noticed that it became 0. Can we add a little check there that's saying if in degree, after reducing the in degree, if in degree is 0, add it to our stack?
Absolutely, Raj. So you are catching on in the most perfect way, because whenever we are making these algorithms, we need to see for space and time complexity as well. So we don't need to search every time every element, because the only change that will happen in the in degree array is in the element that we were working on, right? So since 6 is the only element which got affected due to 4, we'll only check if 6 became 0. Okay, since 6 actually became 0, we pushed it into the stack. If 6 would not have become 0, we would have continued with the process. So all we are checking is, once we remove a connection, we check that has it now become 0. If it has, we push it into the stack. If not, we don't do anything and we continue. Does that answer your question?
Yes, absolutely. That was my question.
Okay, so we continue with the process. So now 6 would go into the stack, right? And now 6 gets popped out. So now we'll remove the connection that 6 had. So 6 is connected to 7. So now the in degree of 7 would become 0, like this. Okay, and now since 7 became 0, 7 will be pushed into the stack. Now again, we'll pop out 7. 7 does not have any outward arrows, so we can continue. Now we'll pop out 1. 1 does not have any 1. Oh, actually 1 does have an outward arrow, which is 3. So now we'll make the count for 3 from 1 to 0, like this. Okay, and then we again push it into the stack. We pop it out of the stack. And we check, do we have any outward arrows? No. Also, this is proved by the in degree, because everything is now back to 0. Okay, so we are sure that whatever we did is correct. We did not have any cycles in the graph, or we did not miss any state. So this is the result that we have obtained.
Shivanku, I was wondering, can you explain me what the time complexity for this algorithm is?
Sure. So the time complexity of this algorithm would be pretty similar to something which is on the lines of counting sort, because if you remember counting sort and radix sort, what we were doing we were basically going over all the elements, counting the number of times that they occur. So something on those lines, when we consider element as V and the edges as E, so the complexity for this would be O of V plus E. So it totally depends on the size of the graph, but usually it ends up being O of V plus E, which is much better. If you remember what professor explained, the example that he took in the class. So those algorithms were V squared or V plus E squared. So this is O of V plus E, which is quite good in terms of space-time complexity. So I hope this concept is clear, because as we can see in Kahn's algorithm, the output that we got is unique because we are working using a stack and we are following an in degree approach. So this is the only result that we can obtain. Whereas in in topological sort, which was using DFS, which was explained by Raj, we could obtain multiple solutions. So this is the most efficient solution which can be obtained using topological sort. This can be obtained using DFS also, but there are multiple other solutions which are possible, which can be obtained from DFS, whereas Kahn's algorithm gives only one solution. Also, Raj, I was wondering if it matters if we use stack, queue, or an array. Do you have any input on this?
That's a good question, Shivanku. So I think what Shivanku is asking is, when we kept adding all the vertices that had an in degree of 0, we used the data structure stack in this example. And does it matter if we use a stack, a queue, or an array in this? So to answer your question, actually it does not. Whether you use a stack or queue or an array, you would have the correct answer. The order would be slightly varied, but you would still have the answer. So I think in this example we saw, there was a situation where 1 was in the stack, and then we took out some edges and we had 6 go up to the stack, and then 6 was popped out. So yeah, right here. So in this example, since it was a stack, we popped 6 out and added 6, but it wouldn't matter if we took 1 and added 1 and then we went to 6 and took out its edges. It really wouldn't matter. The order is still right. We've still covered all the prereqs for 1 or 6 before. So we can pick either one or 6. So it doesn't matter if you use a stack, you use a queue, you use an array list, or any other collection and data structure.
So Raj, if I can relate to what you're saying, so what in terms of courses, so what you're saying is that if I need to complete something, let's say if I need to complete 46A and 46B, so it doesn't matter for how I complete it, as long as I've completed 46A, then I'm eligible to complete 46B, as in it doesn't matter in which semester I did it, right?
Absolutely.
if I took 46A in my first semester, I'm eligible to take 46B in my second or my third semester. So it wouldn't matter when I took it. I could have had Calc 1 in my second semester and 46B in my third semester, or I could have had 46B in my second semester and Calc 1 in my third semester. So keeping that example of classes in mind, it wouldn't matter the data structure that you use.
Okay, so that's it for today. I think these are the main topics that we wanted to cover for today. I really hope that you guys could have a good grip on what graphs are, why they are used, and how topological sort using DFS can be done, how topological sort using Khan's algorithm can be done, and how the results from both are a little different, and when we use one over the other, and how we can visualize these in real world case scenarios. So is there anything else you want to add on, Raj, or we can finish off the session?
I think that's all. It was, I hope this was beneficial to all who came in. Thank you for joining us. And we will have our next SI session on Tuesday at 1 p.m. in person at the Peer Connections. We will be covering the next topic or the next homework that's on Canvas. So I hope to see everyone there. The next virtual SI session would be 2 weeks from today. So not next Friday, but the week after. So I hope to see everyone there as well. If you have any questions, feel free to come up to either Shivanku or I in the class, in any of the SI sessions, and we're more than happy to help you. Thank you for joining us. You can leave the session now.
Thank you.